A few more examples of arc length. We have our function f of x equals ln sec x from 0 to pi fourths. So we use our formula, and remembering that our formula L is going to be integral from a to b square root 1 plus f prime of x dx. And first thing we should probably do is just graph the function. All right, so we'll go to Wolfram alpha, and we're going to graph our ln of sec x, and the domain was from 0 to pi fourths. 0 to pi over 4. All right. And our graph isn't going to be all that spectacular. In fact, it kind of looks like the one that we just did. And it also gives us the length of the curve. Now, be careful of this one, all right? Because it gives you a hyperbolic inverse tangent with the tangent of pi eighths, all right? If you do this by hand, you're not going to be able to get to this answer without several different trigonometric identities, okay? So just beware that even though this isn't a wrong answer, it certainly isn't the one that a student would derive by using techniques of basic interval calculus. All right, so anyhow, we're going to go ahead, we're going to graph it. And here we go. All right, so here's our pi fourths for x. All right, and here is our 0. All right, derivative. This is a chain rule. All right, so the derivative for this is going to be 1 over the secant of x. We know the derivative of ln times the derivative of secant, which is going to be secant tangent. Right? And so this works out really nicely because those cancel out and we're just left with the tangent of x. We're going to substitute that back in. And so we're going to get the integral from 0 to pi fourths square root 1 plus tan square of x dx. Because remember, and I forgot to do this up here, we should square our function, right? Now at this point, we probably remember from our trigonometric substitutions that this is a Pythagorean identity. So this is going to be the integral 0 to pi fourths natural log, or I'm sorry, not natural log, that's the integral of this. Integral of sec square x dx, right? And then we know that the square and the square root are going to cancel out. So really what we get is integral from 0 to pi fourths of sec x dx, all right? And that's a basic one, okay? We could just go onto our card, and we know that the antiderivative is going to be the natural log of the absolute value of secant x plus tangent x. And that's going to go from 0 to pi fourths. All right. So now we're going to substitute. So we're going to get natural log of sec pi fourths. And I got rid of the absolute values just because I know that all the values are going to be positive or at least 0. All right. So I'm not too worried about that. So sec pi fourths and then tan pi fourths minus natural log of sec 0 plus tan 0. All right. So at this point, we have to go through and remember what's happening at 0 on our unit circle, and then also what's happening at pi fourths. All right. So now the good news is we're in quadrant 1. All right. So this is when right here, we have theta is 0. So that's the point 1, 0. And then at pi fourths, which is right about here, we have root 2 over 2, comma root 2 over 2. So we just go to our unit circle. Remember that secant is going to be 1 over the reciprocal. Okay, so if we have secant of theta, in this case, we should probably say theta in this case. So secant of theta in general is 1 over the x coordinate, and then the tangent of theta is y over the x coordinate. And so we're just going to substitute back in. So this becomes natural log of root 2 over, or 1 over the x coordinate, which is root 2 over 2, plus y over x, and again, we're at pi fourths, So that's going to be root 2 over 2, root 2 over 2. Right? Sec of 0 is going to be 1 over the x coordinate, which is going to be 1 over 1. So that's going to be 1 over 1. And then the tangent of 0 is y over x. Y is 0 over 1. All right. So if you've never been too good at evaluating your basic trig stuff, okay, especially without a calculator, this is what you guys should be doing, okay, using a unit circle to be able to calculate those. If we simplify this, natural log of 2 over root 2 plus 1, and then over here, this just becomes natural log of 1. And we know natural log of 1 is going to be 0. If we wanted to rationalize or get a common denominator for this, we could. So I'm just going to say natural log of 2 over root 2. If you want to rationalize, remember you can do that. And so one final way to write this, natural log of 2 root 2 over 2 plus 1, which is the same thing as natural log of root 2 plus 1. All right, now remember that when we went through and looked at Wolfram Alpha's answer, it had this 2 inverse hyperbolic tangent, tangent of pi eighths, or 0.8814. All right, so let's see what happens if I plug in the natural log of square root of 2 plus 1, 0.8814, and down here, 0.8814. So these two expressions are mathematically equivalent. So the 2 inverse hyperbolic tangent, tan pi eighths, is going to be equivalent to natural log of root 2 plus 1. This is a much nicer answer, all right? And again, that's the danger of using your computer algebra system sometimes, is that sometimes they'll give you a nice answer, sometimes they won't. All right, so another example in the next video of our